Hi everybody, I hope this video finds you well. In today's video, we're going to be working through the Practice 5 worksheet. This worksheet focuses on conditional analysis and basic probability. As usual, if you haven't already had a chance to try some of these problems on your own, I would go ahead and pause this video and try as many of these as you can, make some progress on them, and then go ahead and watch this video. If you've already completed these and you just want to sort of check over your work, then we can go ahead and proceed. So let's go ahead and get started with these questions. So for question 1 here, we have an ice cream parlor that is trying out 3 new flavors of quote-unquote breakfast-inspired ice cream. For 1 month, they monitor the sales of these 3 new flavors, and they interview any customers that purchase these, asking, what did you think of this flavor? So they're asking the people who purchased these 3 special flavors, what did you think of the flavor? And they get the following data. So the 3 flavors that it looks like they are trying out are Earl Grey, Blueberry Muffin, and Chocolate Bacon. And then when they asked these people what did they think, they were allowed to say they thought the flavor was very good, good, okay, and bad. Again, this is what we call a two-way table. Remember that the way to think about this is any of these values inside are the frequencies of individuals that had both of these traits or fell into both categories. So in other words, these 101 people here, there were 101 people who had the blueberry muffin flavor and then said that that flavor was good. Okay, so we're going to do some analysis with this, with, of course, ultimately about sort of midway through the problem, we'll get down to constructing the conditional distribution. This is a very sort of typical setup for conditional analysis. Remember, with a two-way table, two-way tables are what we use to display information that has been categorized by 2 categorical variables, and then oftentimes we want to do conditional analysis on that. So we'll go ahead and we'll work on this on the next page, and we'll reference back to these questions as need be. So here's our data here. Remember that the first thing to always do when you see a two-way table is add in the row and column totals and then eventually the table total. So let's go ahead and start by getting the row totals. So 21 plus 28 plus 58 looks like, if we zoom in just a little bit, we should have 107 there. Then 21 plus 101 plus 20. We got 142 there, 35, 36, and 31. We got 102 there, and then 9, 18, and 90. We had 117 there. If we go ahead and do the column totals, looks like we had 21, 21, 35, and 9. So that was 86. Then 28, 101, 36, and 18. That was 183. And 58, 20, 31, and 90, which was 199. Then we can either go ahead and total up those row totals or total up those column totals. Either way we do it, we have to get the same thing. So I'll go ahead and just add these, so we only have to do 3 additions. So 86 plus 183 plus 199, so 86 plus 183 plus 199. Looks like we should have 468. So remember, what this 468 represents is the sample size. In this case, it represents the number of customers that came in and ordered one of these 3 flavors and then gave their feedback about these flavors. Okay, so no matter if we haven't even looked at the questions, but we know that we want to go ahead and do this to start with. So let's go ahead now and look at what the questions were. So for part A, we wanted to know which ice cream flavor was the most frequently purchased during this month. So if we look back here, we can see that 86 people purchased Earl Grey, 183 purchased the Blueberry Muffin, and 199 purchased the Chocolate and Bacon. So it's close, right? Blueberry Muffin 183 versus 199, but Chocolate Bacon was the most frequently purchased. So most frequent flavor would be that Chocolate Bacon, right? With Blueberry Muffin being a close second and Earl Grey being a distant third. Earl Grey had below 100 purchases during that time frame. All right, let's see what else we want to do. For part B, we want to get the percentage of customers in your study. So we notice that this is a percentage of the customers in our study, so we know it's going to be out of the total, who chose Earl Grey and thought the flavor was okay. So we want the percentage of study who picked Earl Grey and said okay. So in other words, they had to have tried the Earl Grey flavor and then ultimately said it was only okay. So of course, here's all the people who picked the Earl Grey flavor. Here's all the people who said that it was okay. So that means it would be those 35 individuals. Only 35 people tried the Earl Grey and then followed up by saying it was okay. So it would be that 35 divided by the 468. We're dividing by 468 because it says the percentage of the study, so of everyone in the study. 35 divided by 468, and then we'll convert that into a percentage. Looks like we should get about 7.5%. So about 7.5% of everyone in the study ended up being people who had chosen the Earl Grey flavor and then followed up by saying that that Earl Grey flavor was only okay. All right, for part C, I think we have something similar. We want the percentage of customers in your study who chose chocolate bacon or thought the flavor they got was very good. So again, it's going to be the percentage of study who picked chocolate bacon or said very good. Okay, so we have to be careful here. The percentage of people who picked chocolate bacon or said very good, we know that or generally indicates an addition. So where are all the chocolate bacon people? Well, they're right here, 199. Where are all the very good people? Right there, it's 107. The only thing we have to be careful about is that to get all the chocolate bacon people, we added that up. To get all the very good people, we added that up. So notice that those 58 people there, those people who picked chocolate bacon and said that chocolate bacon was very good are sort of being double counted. So we have to be careful about not double counting them. So to do that, we can easily do this as 199, which is the total for chocolate bacon, plus the total for very good, which is 107. But then because that does double count these 58, we simply subtract the 58 and then divide by 468 still. Now, of course, if you don't like this, this numerator could also be found by simply adding up 21, 28, 58, 20, 31, and 90, which would be anybody who said very good or had chocolate bacon. Either way, if we go ahead and add this up, 199 plus 107 minus 58 should give you a numerator here of 248. Divide that 248 by 468, and we should get that this is approximately, after rounding, 53.0%. So basically about 53% of everybody in the study either picked chocolate bacon as their flavor or ended up saying whatever flavor they had was very good. All right, I think we're ready now to go ahead and do the conditional. Notice that anytime you're asked to build a conditional distribution, it's always based on one of the two variables. You always have to have one of the variables as the explanatory. In this case, it says construct the conditional based on the choice of flavor. So we're conditioning on choice of flavor, which makes sense, right? We would think that the flavor you choose might impact your review. It wouldn't really make sense to say that your review impacts the flavor you chose because, well, you choose the flavor and then you review it. So it makes sense to use taste as the explanatory here. So conditional based on flavor. Flavor was located in the columns, so we're going to go ahead and divide by the column totals. So we'll take each of these values and divide by their corresponding column total there. So we'll rewrite our table. I'll do some abbreviations. And we have very good, good. Oh, I zoomed a little too far there. My apologies. Okay and bad. And then we have our chocolate bacon. Earl Grey was first. Earl Grey, our blueberry muffin, and our chocolate bacon there. Okay, we'll reconstruct the table. Remember, for doing a conditional distribution, we're only interested in the values inside the table, so we don't have to worry about calculating percentages for the totals or anything like that. All right, so for this first column, we'll divide everything by 86. So 21 divided by 86 should give us 24.4%. The next one is also going to be 24.4%. For OK, it should be 35 divided by 86, which would be 40.7%. And then 9 divided by 86 should give us 10.5%. So this is basically telling us the sort of review breakdown for this particular flavor. Of the people who had Earl Grey, 24.4 said very good, 24.4 said good, 40.7 said okay, and only 10.5 said it was bad. All right, let's go ahead and do the blueberry muffin one, where we'll divide everything by 183. So 28 divided by 183 should give us 15.3%. 101 divided by 183, 55.2%. 36 divided by 183 should give us 19.7%. And then 18 divided by 183 looks like we should have 9.8%. So once again, this gives us sort of the review breakdown for this blueberry muffin flavor. 15% said very good, 55% said good, 19.7 said okay, and 9.8 said it was bad. For chocolate bacon, we'll go ahead and divide everything by 199. So 58 divided by 199. So that would be 29.1%. Then 20 divided by 199 should give us 10.1%. 31 divided by 199 gives us 15.6%. And then finally, 90 divided by 199 gives us 45.2%. So once again, that gives us the sort of review breakdown for this particular chocolate bacon flavor. All right, now for the remainder of the sort of questions, we're going to make use of this conditional distribution and analyze this a bit with probably the hopes of trying to figure out which of these flavors is proving to be the most successful. So let's see what else we have to do here. We want to know which flavor had the highest rate of customers that thought the flavor was very good, and we want to say what that rate was. So for part E, we want highest rate of very good, which of course is the best review. So we're looking here. Earl Grey got 24.4%, blueberry muffin only 15.3%, and chocolate bacon 29.1%. So it would be chocolate bacon with 29.1%. So in other words, close to 30% of everyone who had chocolate bacon rated it as very good. Only a little less than a quarter of the people who had Earl Grey said it was very good, and only about 15% of the people who had blueberry muffin said it was very good. So in terms of the best possible review, chocolate bacon seems to have the highest rate of that. All right, let's go ahead and look at what we want to do in F. For F, we want to say which flavor had the lowest rate that thought the flavor was bad. And again, we want to say that. What was that rate? So lowest rate of bad. Now, since chocolate bacon had the highest rate of very good, does that guarantee that it has the lowest rate of bad? Well, of course not, because there's not just two options. It's not like you got to say very good or bad. There's all these other options like good or okay in between. So this is its own unique question. For the lowest rate of bad, we can see that Earl Grey had 10.5, blueberry muffin was just barely lower at 9.8, and chocolate bacon was way up at 45.2, which is not a good sign, right? That means a lot of people didn't like that flavor. So the answer here would be the blueberry muffin with only 9.8%. So in other words, under 10% of the people who had that blueberry muffin flavor actually ended up saying it was bad. Okay, so let's put all of this together into the last part here. In part G set, it says if the ice cream parlor wanted to keep only one of these flavors, so they're experimenting with 3 and they want to narrow it down to just keeping one of them, which would you recommend based on this data? And we want to make sure to give at least a 1-sentence justification based on the data. So let's go ahead and just talk briefly about what we might be sort of seeing here. And of course, we want to focus mostly on this conditional, but we might also want to consider some of the information here, especially about the sort of frequency of the purchases. So if we look at these flavors, right, we can sort of see that if we start one by one, well, right here we see a good argument for chocolate bacon. Chocolate bacon, of course, had the highest rate of very good. 29.1% of people, the largest rate of the best possible review. The downside, of course, for chocolate bacon is that it had the, by far, almost half the people that had it didn't seem to like it, 45.2%. These guys are not even close to that. So that's pretty worrying. That means that there's some people who really like the flavor, but a lot of people really don't like the flavor. Was chocolate bacon a popular flavor? Forgetting about the reviews? Well, it was. A lot of people did decide to purchase it, so it clearly sort of stimulated a lot of interest, but ultimately we'd have to be pretty concerned about having nearly half the people who tried it not like it. You probably don't want people trying something at your restaurant or your ice cream parlor and then ultimately saying, well, yeah, I tried it, but I didn't like it. That's not going to bring them back. What about this Earl Grey flavor? Well, Earl Grey had some positive things. I mean, it was second in very good. It was second lowest in bad, so those are good signs. Notice it had a high percentage of okay, which is probably not something we're really looking for. We don't really want to be known as like the okay ice cream parlor. But there's something really worrying about Earl Grey, and it's back up here. Remember that Earl Grey was by far the least frequently purchased, meaning that it just didn't motivate customers to want to buy it. Forget about how they reviewed it. People just didn't seem to want to try it, forgetting about how they actually, it did okay when people did it, or when people tried it, but it just didn't seem to motivate a lot of interest. So we'd be a little concerned about Earl Grey. That leaves us with this blueberry muffin flavor, which seems to have a lot of things going for it. First of all, it was the second most purchased. It was just a little bit behind chocolate bacon, so it's surely stirred up a lot of interest. Second, it had the lowest rate of bad, which is really good. And while it didn't have a very high rate of very good, it did have a very high rate of good. And you can also see that if you put these two together, very good and good, which you could probably think are the two really sort of positive responses, it does have the highest combined rate. If you add these together, that's 48.8%. If you add these together, it's 70.5%. And if you add these together, it's 39.2%. So Blueberry Muffin has the highest combined rate of the two positive reviews. So all of this would probably indicate that Blueberry Muffin is the best flavor to keep. So we could go with Blueberry Muffin, since it was the second most purchased, had the lowest rate of bad reviews, and it had the highest combined rate of very good / good reviews. So all of that would be a strong argument for Blueberry Muffin. Could you maybe try to argue for the other ones? Perhaps, but as we said, there's some big limitations to those. People who would argue for chocolate bacon are basically acknowledging that close to half the people that are going to try it are going to end up saying it was bad. That's probably not something you'd want as your customer experience. And for Earl Grey, while it had pretty decent reviews, it had a large percentage saying only okay, and really worrying is that it just not a lot of people seemingly wanted to purchase it. So Blueberry Muffin has a lot of strong positives here, and this combined rate of the two positive reviews, very good and good, is really a good indicator. Also keep in mind, it's not just the highest combined rate by a little bit, it's the highest combined rate by a lot. This was 48.8, this one, like we said, is 70.5, and this one is 39.2. This by far and away had the highest combined rate of very good and good. Okay, so that was quite a bit there, but that hopefully gave you guys a good amount of practice working with the conditional distribution and conditional analysis when we have these two-way tables. The remainder of the problems on this practice focus on basic probability, so let's go ahead and get started on those. So for question 2 here, we have this special deck of cards. To make this a little bit easier though, even though these are how the questions were written on there, let's go ahead and just give ourselves a fresh page just to work on this one. So for this question 2, we have a special deck of cards. This deck consists of 10 cards that have squares on them. So for these 10 cards with squares, 2 are blue, 2 are red, 2 are green, 2 are yellow, and 2 are black. So 2, 4, 6, 8, 10. Yep, that does add up to 10. 8 cards with triangles on them, 2 blue, 2 red, 2 green, 2 yellow. 8 cards with circles, 2 blue, 2 red, 2 green, 2 yellow. And 6 cards with arrows, 2 blue, 2 red, 2 green. So we're going to suppose that you select one card at random from this deck. Okay, so the first thing we probably want to make a note of is we'd probably like to know how many cards are there in this deck. So we know there's 10 with squares, 8 with triangles, so that's 18. 8 with circles, that's 26, and 6 with arrows, that's 32. So we have 32 cards overall. Why is that 32 cards overall important? Well, in our sort of probability terminology, that would be the size of the sample space. There are 32 different cards you could end up choosing from this deck, and each of those cards are equally likely. So we've got a bunch of probabilities to calculate here. Well, let's go ahead and get the probability that we end up getting a circle. So what's the chance we get a circle? Well, we know it's going to be out of 32 because there are 32 cards overall. How many circles are there? Well, we know that there are 8 circles. 2 blue, 2 red, 2 green, 2 yellow, but of course we don't care about the color, we just want it to be a circle. So it's going to be those 8 cards with circles. So 8 out of 32. Can we simplify that? Can we turn it into a decimal? Can we turn it into a percentage? For sure, we can do all those things, but we don't need to. This, in some ways, is the best format because it shows us what the probability is really calculating. It's saying there's 8 circles out of 32 total cards. All right, let's go ahead and get the probability that we get a yellow card. So how can we determine that? Well, we need to figure out how many yellows there are. So there are 2 yellow squares. There are 2 yellow triangles, so that's 4 overall. There's 2 yellow circles, that's 6. And there are no yellow arrows, so we have 6 yellow cards overall. So this would be 6 out of 32. Still out of 32 because, again, there's 32 cards overall. All right, let's go ahead and this would be part C here. We'd like to get the probability of blue or black. So we're saying we're okay with either color, either blue or black. So let's think about the blue. We know that OR generally indicates addition. Remember, there's the addition rule for OR. Let's go ahead and see. For blue, we know that there are 2 blue there, 2 blue there, 2 blue, and 2 blue. So that's 8 blue overall. Plus, how many black cards are there? Well, there's 2 there, none here. None here and none here. So there are just 2 black cards overall, plus 2. Do we have to worry about any sort of subtraction? Is there any overlap? Well, no, right? We know that these 2 are what we would call mutually exclusive, right? There are no blue and black cards. There are no cards that have both those colors on them. So there's no overlap here. We don't have to subtract anything. So we just simply divide by 32. And we can say that that's 10 out of 32. So the probability that we get a blue or black card, 10 out of 32. All right, let's go ahead and take a look at the probability that we get a triangle or green. Okay, so again, this is one where we sort of know that we're going to need to add. How many triangles are there? Well, if we look, we know that there are 8 cards with triangles. So we can say 8 plus. How many greens are there? Well, it looks like there's 2 greens there, 2 greens there, 2 greens there, and 2 greens there. So another 8, so plus 8. Now, is there any overlap? Are there any triangles that are also green? Well, yeah, there's 2 green triangles, and we double counted those. We counted them once when we said that there were 8 triangles, and we counted them again when we said that there were 2, 4, 6, 8 green cards. So we need to subtract that. That's the addition rule. So we're subtracting that, divided by 32. We should get 14 out of 32 there. All right, let's go ahead and look at E. For E, we want the probability that we get a square and red. So it needs to be both a square and red. So it has to have both of those traits. So we know that there are 10 squares, but only 2 of them are red. So only those 2 will satisfy what we want. So that would be 2 out of 32. There are only 2 cards that are simultaneously squares and red. All right, for F, we want it to be an arrow and black. Well, if we go here, we can see that there are 6 cards with arrows. There are 2 blue, 2 red, and 2 green, which means there are no black arrows here. So that means that this would be 0 out of 32, or just 0. That means that these 2 events cannot happen at the same time. Remember, 0 indicates an impossible event. In our terminology, we would call this mutually exclusive. You cannot get an arrow card and a black card at the same time. There just simply aren't any cards that'll do that. All right, we've got another one here. G, the probability you do not get a red card, so probability not red, well, we can simply, we could certainly go up and count up all the other colors, but this is something where we can use that complement rule and make it a little bit easier. So we do 1 minus the probability of red, which is 1 minus, what's the chance we get a red card? Well, there are 2 reds there, 2 reds there, 2 reds, and 2 reds. So that's 8 overall. So 8 over 32. You can, of course, make a common denominator by thinking about this as 32 over 32 minus 8 over 32. And that would be 24 over 32. All right. And then one more sort of similar to that. We have the probability that you do not get a triangle. So not triangle. We can do the same idea, use the complement rule, do 1 minus the probability we do get a triangle, which is 1 minus. Well, if we go up here, how many triangles are there? We know there are 8 cards with triangles. So 1 minus 8 over 32. And again, by making the common denominator, viewing that as 32 over 32, you should get 24 over 32 overall. Okay, so there we go. A bunch of sort of basic probability calculations using some of the basic probability rules, like the addition rule and the complement rule. Also keep in mind that, sort of one common trend here. Notice that every one of our answers was out of 32, because since we were just selecting one card out of this entire deck that had 32 cards in it, we were always having 32 different options, so everything was going to be out of 32. All right, well, let's go ahead and take a look at the next sort of basic probability one, which has us building a probability model. So for question 3 on here, we have 2 fair dice, and one of them is 6-sided, which is labeled 1 through 6, but one is only 4-sided, labeled 1 through 4. And what we do is, once we roll the 2 dice, we record the maximum of the 2 dice. So that means that if, we roll a 3 and a 4, we would count that as a 4, because the maximum of 3 and 4 is 4. If you roll a 2 and a 2, well, you would record a 2, because the maximum of 2 and 2, the biggest one you rolled, was 2. So you're always just choosing the largest number you rolled. So we're going to calculate some probabilities down here, but what we're going to do first is we're going to try to write down a probability model for this. Remember, a probability model means all the possible outcomes and their associated probabilities. Generally, anytime we see something like with 2 dice, or anytime we're doing 2 things and we are sort of combining them together according to some rule, recording the maximum in this case, we like to sort of draw out a little diagram that helps us organize everything. So let's go ahead and do that here. Let's put our 6-sided dice here. 1, 2, 3, 4, 5, 6. Those are all the things that can happen there. And let's put our 4-sided dice here. 1, 2, 3, 4. And then we'll put some lines. And on the inside of this table, we'll put the actual result of this game or of this rule. So remember, in this one, you record the maximum of the 2 dice. So 1 and 1, well, the maximum would be 1. 1 and 2, the maximum would be 2. 1 and 3, 3. 1 and 4, 4. What happens with 2 and 1? Well, 2 is the biggest one, so 2. 2 and 2 would be 2. 2 and 3 would be 3. 2 and 4, also 4. We're just recording whatever the largest one is. 3 and 1 would be 3. 3 and 2 would be 3. 3 and 3 would be 3. 3 and 4 would be 4. 4 and 1 would be 4. 4 and 2 would be 4. 4 and 3 would be 4. 4 and 4 would be 4. Of course, 5, there's no way you can get anything larger than 5 on the 4-sided dice, so 5 is always going to win out then. Same thing with 6 here. So, looking on the inside here, it looks like the possible results are 1, 2, 3, 4, 5, or 6. So if we go to write down our model for part A here, the outcomes, and of course their probabilities. Our outcomes are 1, 2, 3, 4, 5, and 6. For their probabilities, what are all the probabilities going to be out of? Well, we had 6 options here, 4 options here. 6 times 4 is going to give us 24 options. You can also just go through and count that there's 24 things in here, but everything's going to be out of 24. How many ways were there to get 1? Well, it only showed up once, so the probability would be 1 out of 24. To get a 1, you had to literally get a 1 and 1. To get a 2, you can get it 3 different ways. So it would be 3 out of 24. For 3, it looks like you can go 1, 2, 3, 4, 5 different ways. So 5 out of 24. For 4, we had 1, 2, 3, 4, 5, 6, 7 different ways. So 7 out of 24. For 5, we had 1, 2, 3, 4. So 4 out of 24. And for 6, same thing, 4 out of 24. Because for 5 and 6, it doesn't really matter what you get on the 4-sided dice. As soon as you get that 5 or 6, then we know that that's going to be the maximum. Can we check that these all make sense? Well, yeah, they're all numbers between 0 and 1, so they satisfy the first rule of probability models. And if we sum these up, 1, 4, 9, 16, 20, 24, they do add up exactly to 1. So that confirms that this thing really is a probability model. All right, let's go ahead and use this to answer some questions. We want to get the probability that we get an odd. So which of these outcomes are odds? Well, it would be the 1, the 3, and the 5. So this is the same as basically saying 1 or 3 or 5. Obviously, 1, 3, and 5 are all mutually exclusive. You can't get a 1 and a 3 or a 1 and a 5. You either get a 1 or a 3 or a 5. So we can just add the probabilities together. 1 out of 24 plus 5 out of 24 plus 4 out of 24. And if we do that, that looks like we should get a total of 10 out of 24. Again, remember, this is also why we don't simplify these fractions. Like certainly 4 out of 24, you could simplify to 1/6, but you don't really want to do that. You want to keep the denominators the same so it's nice and easy to add them together. All right, for C, we want to get the probability we get a number greater than 2. So greater than 2 would be 3, 4, 5, or 6. Remember, 2 would not count as being greater than 2. Okay, so 3, 4, 5, and 6, all mutually exclusive, so we can go ahead and add these together. 5 out of 24, 7 out of 24, 4 out of 24, and 4 out of 24 again. So adding those up, we get 5, 12, 16, 20. So we got 20 out of 24 there. Okay, what else did we want to do? We wanted to get the probability you record an odd number and a number greater than 2. So we want to try to put these events together and see when that can happen. So odd and greater than 2. Remember, this and means it has to have both these traits. So it has to be odd, so 1, 3, or 5. And it has to be greater than 2, so 3, 4, 5, and 6. Clearly, the overlap is just the 3 and 5, right? The 1, while it's odd, is not greater than 2. And the 4 and 6, while greater than 2, are not odd. So the only ones that'll work here are 3 and 5. They are both odd and greater than 2. So it would be 5 out of 24 plus 4 out of 24, which would give us a probability there of 9 out of 24. Notice that this probability has to be smaller than these guys here, because for this to happen, you have to achieve both of these things, which should be harder to do, which means that the probability should be lower. Remember, a lower probability indicates that the event is less likely to happen. And it should be harder to have both of these things happen than it is to have just one of them happen. Finally, for part E here, we want to calculate the probability you record an odd number or a number greater than 2. So now we're saying we don't care if it's odd or if it's greater than 2. We want it to just be 1 or both, or either way. So to do this, of course, we could just try to list out all the numbers that are odd, 1, 3, 5, all the ones that are greater than 2 that we haven't already listed, 4 and 6, or we can use the addition rule if we like. So we can say that this is the probability of odd plus the probability of greater than 2 minus the probability of odd and greater than 2. That's that addition rule. The reason I'm actually writing out the whole addition rule is that we actually just calculated all three of those things, so we might as well use them. So we would get 10 out of 24 plus 20 out of 24 minus 9 out of 24, which would ultimately give us 21 out of 24. Now, could we get the same thing if we just came up with the actual outcomes and just did it manually? Sure, right? The odds would be 1, 3, 5. The greater than 2s would be 3, but it's already listed. 4, 5, but it's already listed. And 6. So it would be 1, 3, 5, 4, and 6. If we just do those, it would be 1, 6 out of 24, 13 out of 24, 17 out of 24, 21 out of 24, which, of course, is the answer we got there. All right, last one, which is a little beyond where we're currently at. If you've watched up through like the basic probability part 3 video and everything. But let's go ahead and see this, as it'll sort of give us what we're going to be doing as we move into advanced probability. We're going to suppose that the 6-sided dice comes up a 2, and we're going to calculate the probability that you record a number greater than 2. So we're basically saying here the probability that we get greater than 2, given that, what do we say, the 6-sided dice, given that d6 comes up as 2. Now, in our advanced probability discussion, this will be what's called a conditional probability, because there's extra information. We know that the d6 comes up as a 2. Well, let's think about how we can just sort of reason this out. If the 6-sided dice comes up as a 2, we sort of know we don't have our full diagram anymore. We know on the 6-sided dice that we ended up with a 2, meaning that the only things that are still possible are the things in this row, because this row corresponds to when we get a 2 on the 6-sided dice. Now remember, the event we're looking at is that we record a number greater than 2. Well, that would be the 3 or the 4. So does that mean it's 2 out of 24? Well, no, because there's only 4 options now. By knowing that this is going to happen, it's restricted our attention to just these 4 possible outcomes. So there are 2 things that give what we want, greater than 2, out of 4 total things. So the probability here should be 2 out of 4. Now, we will investigate this further in the advanced probability section of our course, where we'll talk about what are more formally called conditional probabilities. So this is something we'll investigate more. This was just sort of a glimpse at that as we move towards advanced probability. All right, let's wrap up this worksheet with the last question, which involved a discrete random variable. So for question 4, this was a discrete random variable, which is sort of the intersection of statistics and data with probability. So in this one, we were supposing that El Camino is interested in studying how many math classes students end up completing by the time they graduate. So El Camino conducts a large study at the next graduation. They ask all the graduating students, how many math classes did you successfully complete at El Camino College? So they get the following data. So for some, there were 0 classes completed, and the probability is 0.04. For 1 class, it was 0.11, 2, 0.39, 3, 0.18, 4, 0.17. For 5, that value is missing, and then for 6, it is 0.01. So what we're going to do with this is sort of the standard analysis we do with these discrete random variables. We're going to end up drawing in a probability histogram, calculating mean and standard deviation, calculating a probability, etc. But we have to do one thing that's a little bit unique, which is to fill in the missing value. So let's give ourselves a fresh page and talk about how to do this. So how can we find this missing value? Well, remember, this is supposed to be a probability model. So we know that these numbers have to sum up to 1. So whatever is left over after we add these up and subtract it from 1 should be what we need to put here. So what we can do is we can simply take like 1 minus and add up all these things. And what we're doing by doing that is guaranteeing that whatever we put here will cause everything to sum up to 1. So if we do that, 0.04 plus 0.11 plus 0.39 plus 0.18 plus 0.17 plus 0.01, what we should see there is we get 1 minus 0.9, which means that that missing value should be 0.1, or if you prefer, 0.10. Okay, now if you want, you can check. If you add all these up, then it will actually sum up to 1. So if there's ever a missing value in a discrete probability model, you can go ahead and fill it in by just figuring out what remains if we need to hit for it to sum up to 1. Could we have used this trick if this one was missing as well, so if both of these were blank? Well, no, we wouldn't be able to, because while we would know what these two would need to add up to, we wouldn't know how they should be distributed. So this is something that can only work if there's a single missing value. All right, for B, I believe we wanted to put this into a probability histogram format. Remember, a probability histogram is very similar to a normal histogram. The probabilities take the place of the frequencies, and these, which means that these will be on your vertical axis, and these guys will be on your horizontal axis. The only difference is that since these things are discrete rather than a whole interval, we're going to label the middle of each bar with these values. So let's go ahead and draw this. So, like we said, we'll put the probabilities where the frequencies would normally go. Looking here, it looks like we have to go as high as 0.39. So we might go like by 0.05. So 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, and 0.40. So 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, 0.40. If you don't like working with the decimals here, you could of course convert all these into percentages, like 4%, 11%, etc., and use the percentages there as well, because remember, probabilities can always be displayed as percentages, decimals, or fractions. All right, let's go ahead and draw our bars. So our first one is 0.04, so our first bar should be there. And then in the middle, we can just label 0. Then our next bar, and remember the bars should touch because it's a histogram, should go up to 0.11, so there. We can label that one as 1. Again, we're just labeling the values in the middle because it's discrete. Then 0.39 all the way up there. So that's the second one. Then 0.18. There we go. There's the third one. 0.17 for the next one, so it's just barely below. And then 0.10. So there we go. And then our next one, 0.01. So way down there. There we go. We should go ahead and label this axis. This is number of math classes completed. All right, I think that's all we wanted to do. Sometimes we're asked to describe the shape of these. This one doesn't have a super strong shape. It might be maybe slightly right skewed, though it does have a bit of a tail to the left, so maybe you could argue that it's normal, though it doesn't really look too balanced. But shape wasn't asked for here, so we don't need to worry about that. Now for C and for D, we want to calculate the mean and the standard deviation of this random variable. So remember that the way we do that is we take this stuff and we put this into L1. We put the probabilities into L2, and we do our 1 var stat L1 comma L2. Now remember, this is the notation that you use if you have a slightly older TI calculator. If you have the slightly newer calculator, you just simply specify that the frequency list should be equal to L2. So we're using that frequency list feature here. So let's go ahead and do that. So we'll hit stat edit in L1. If you have any data in there, you can clear that out. If you have any data in L2, clear that out as well. Then in L1, put in the values for the variable, so 0, 1, 2, 3, 4, 5, and 6. Then corresponding to that in L2, put those probabilities, so 0.04, 0.11, 0.39, 0.18, 0.17, 0.10, and 0.01. Then you can hit stat calc 1 var stats. Again, if you have the slightly newer one, there is a spot to put in a frequency list, so it's just put L2 there. If you have the older one, you have to manually type in L1 comma L2 after hitting the 1 var stat. Either way, you can either hit calculate or hit enter again, and we want to record the mean, which in this case looks like it comes out as equal to 2.67. And remember, it'll be the population standard deviation. That's actually the way you can know that you did this correctly. Sample standard deviation should be blank, and your n should be 1 because you have added up all the probabilities, which sums up to 1. So the standard deviation here should be 1.32. What are the units here? Well, we're measuring the number of math classes completed, so each of these would be in classes. So the average amount of math classes completed, according to our data, is 2.67, where the standard deviation is 1.32 classes. All right, we've got a couple last little things to wrap up here. We want to calculate the probability that a person completed at least 2 math classes. So let's see how we do that. Probability at least 2 math classes. So which of these outcomes up here would satisfy at least 2? Well, that would be 2, 3, 4, 5, and 6. So one way we could do this is we could say that this is equivalent to 2, 3, 4, 5, and 6. And then since each of those are mutually exclusive, we could go ahead and add up all those probabilities. Of course, if you wanted to be a little clever, a little faster about it, you could use the complement rule and do 1 minus the probability of any outcome that isn't on this list. Remember, this list was 2 through 6, so the things not on there would be 0 and 1. So we can use the complement rule to make the event a little simpler, just 0 and 1. Then we can say that that is 1 minus. For 0, the probability was 0.04, plus the probability for 1, which was 0.11. So we put those together, and you should get 0.85. So the probability that we get at least, that a student takes at least or successfully completes at least 2 math classes is 0.85 according to our data. Now, do you get 0.85 if you just simply add up all these? For sure. It's a little bit more work, but not super bad to do it that way either. All right, last little bit, which is a little bit of a statistical analysis question. We're going to say a researcher looks at this data and makes the claim, according to the data shown, 4% of graduating El Camino students never take a math class. Is this claim justified? Why or why not? And our hint is think carefully about the question that was asked. So where is this 4% coming from? Well, they're saying that these 0, the people who completed 0 classes was probability 0.04, and of course 0.04 does become 4%. So it seems to sort of make sense there, but we have to be very careful again about the question that was asked. Notice that the question that was asked was, how many math classes did you successfully complete? Well, that's a little bit different than saying, according to this, that 4% never take a math class. Right? Successfully completing versus taking, 2 very different statements. So while the 0.04 is 4% mathematically, this statement doesn't match the question or the sample that was actually gathered. So our statement in F here would be, no, this statement is not justified. Right? Students were asked how many completed math courses, not how many taken. So, in other words, we're saying that there might be a percentage of students who took a math class, did not successfully complete it, but still graduated. So that means that the researcher's claim of saying that the 4% who never completed one is not the same as saying that 4% never take any. So just being, again, very careful anytime we're working with actual data to make sure that the way somebody is interpreting their conclusion actually matches how they gathered the data or the questions that they were asking. So this wraps up practice 5.